Today we're going to use transformations on quadratic functions using the vertex form. It's first of all important to understand what the parent function of a quadratic looks like, and that's going to be f of x equals x squared. The shape of a quadratic function is what's known as a parabola, and there are several examples drawn over on the right. You can see the highest and lowest points. There's a high point on this parabola, there are low points on the other three. That point is what's known as the vertex, and that's why we're going to be using vertex form today. In order for us to get from what's known as this parent function here over, for example, to this parent function, to this new function, this transformation where we're at 6, -4, we would have to shift 6 units to the right and 4 units down. So we are going to shift h units horizontally, and we are going to shift k units vertically. So to take that parent function x squared, we can put in a minus h and a plus k to talk about how we are going to shift things. We can also talk about the amplitude, which is going to have a vertical stretch, shrink, or reflection. When we look at these 4 examples over here, we can see that from the origin, the vertex at the origin 0, 0, to come to this function, we had to shift 6 units to the right and 2 units up. So h is 6 and k is 2. H is 6 and k is -4. And h is -3, k is 0. We can also talk about the amplitude here. You might notice that this darkest one looks to be a little bit wider. We'll talk about how we find that value in just a moment. We can also talk about the fact that this parabola is upside down. That's going to correspond to a negative amplitude, and we'll talk about specific numbers in just a moment. In general, there is no restriction on the domain. You can plug in anything for x and square it, and you can subtract anything from x and then square it. You can add any value. So we're always going to have domains that run from negative to positive infinity. However, the range are the y values, and if we notice, we come from a low point of -4, and then we are increasing forever. We come from a low point of 0 and are increasing forever, and from the lowest value at the vertex of 2. Well, these are the k values at the vertex. So in general, we can go from k to infinity, including k, but the upside down parabola is coming from -infinity, so we could also say that we could come from -infinity to k. So to consider a couple of examples, what happens if we have a function where it's x minus 2 squared plus 1? It should tell us to shift 2 units right and up 1. And we can start to plug in a few values. We're at 2, 1 for our vertex. What happens if we plug in a positive 1? 1 minus 2 is -1, -1 squared is 1, and 1 plus 1 is 2. So at 1, 2, we should have a point. We can do the same thing with 3. 3 minus 2 is 1, 1 squared is 1, and 1 plus 1 is 2. So 3, 2 is a point on our graph. And, excuse me, what I really want to start to point out here is that parabolas are symmetrical. There's an axis of symmetry, and we can start to get a feel for how this is going to graph. We can continue to plug in values like 0. 0 minus 2 is -2, squared is 4, and 4 plus 1 is 5. We shouldn't have to plug in the 4. We should trust our symmetry I don't exactly have that amount of room on my graph, but I wouldn't eventually. We're going up towards positive infinity. It doesn't take long before we're off the limits of our page here. We're going to go from negative to positive infinity for our domain. And if our low point is the k value, then we do actually get there, and then we start to shoot up towards infinity. We're going in two directions towards infinity, but we only need to write our range once. Another example, x plus 3 squared minus 1. It would be nicer if we were able to say x minus h squared. So without too much trouble, I'm going to switch that plus 3 to a minus negative 3. I don't need to do that all the time, but at the outset, I like to do that just to remind myself that my vertex is going to be located at negative 3, negative 1. You can check to see if we plug in a negative 3, we're going to come up with 0, 0 squared, and minus 1. So at negative 3, negative 1, we're going to have our graph, our vertex, and we're going to still orient ourselves upward. We have an amplitude of a positive 1. So we're going to start to shoot up like that. We've shifted 3 units to the left and 1 unit down to get to our vertex. Our domain is still unlimited, but our range now comes from negative 1 and shoots up towards infinity. To speak just very briefly about the amplitude, it's the same situation as when we were talking about it with relation to the absolute value. If our value for A is greater than 1, when we take the absolute value, then we're going to have a vertical stretch. Because we're going to take values of whatever's inside the parentheses squared, and then when we multiply, that increases. So, for example, if our amplitude is 3, 0 squared is still 0, and 0 times 3 is still 0. So we would still be in this location. But to plug in a 1, 1 squared is 1, and 1 times 3 is 3. So we're going to be vertically stretched. Points that were here on our parent function are now stretched up by a factor of 3. If our value of A is between 0 and 1, then we're going to have a vertical shrink. And we're going to draw things down. Instead of going over 1 and up 1 on our parent function, we're going to go only up a half of a unit. And you can see how we are being pulled down. Instead of going all the way up this far, we're only going up half as far for the x from the x-axis. And finally, if our amplitude is negative, we're going to have a reflection so a negative amplitude is going to flip us vertically. It doesn't matter if it's a negative 1, a negative 1/2, a negative 7. It's still going to flip vertically. Because I have the 4 in there, there's two things going on. I'm going to be oriented downward, and I'm also going to be stretched. I'm not being super specific here, but I have a sense of how this is going to graph. So when I go to plot in vertex form, I want to take note, first of all, of where my vertex is. I'm going to be at 1, 3 here. So I want to come to 1, 3. My amplitude tells me that I'm going to be oriented downward and stretched. And I can plug in something very close. Like let's plug in the value of 2. 2 minus 1 is 1. 1 squared is 1. 1 times negative 2 is negative 2. And negative 2 plus 3 is 1. So I should be coming down like this for my first graph. The symmetry tells me that if I've come 1 unit off of the axis of symmetry, then I should come 1 unit over here, and I can get a sense of how that's going to graph. I'm going to continue to come down forever, but that's a good sense of how that's going to graph. For my second example, I wish I had my h value I don't, unless I put it in the parentheses, and I can say that's x minus 0. So my vertex is going to be at 0, negative 2. I've only shifted down 2 units. I have not shifted left or right. My positive 1/2 for my amplitude tells me that I'm still going to be oriented upward, but I'm going to only have a vertical shrink. I'm going to look wider than this. So you can plug in whatever values seem to make sense to you. If you want to plug in a 1, 1 squared is 1 times 1/2. So that's 1/2. 1/2 minus 2 is negative 1/2. So if we come over to 1, we should be down at negative 1/2, and the symmetry would tell me where I would want to be on the other side of the axis. If I plug in a 2, 2 squared is 4, 1/2 of 4 is back to 2, and 2 minus 2 is 0. So here's my second function. Finally, there's a challenge here. Can we come up with the equation of the parabola that passes through negative 2, 1, and also has the vertex of 1, 4? So we're reminded of vertex form, and we can plug in the 1 and the 4. So we're in good shape, but there's still a problem, and that is I'm not sure what my amplitude is. So how do we figure out A? Well, there's information that we haven't used yet. It passes through the point negative 2, 1. 1 is our y value. Negative 2 is our x. And so we should be able to plug those in. And now the only unknown is A. Negative 2 minus 1 is negative 3. Negative 3 squared is 9. If we subtract 4 to the other side, we'll get negative 3 equals 9a. A little bit of division, and a is going to equal negative 3/9 or negative 1/3. I feel pretty good about that because we're oriented upside down, and if this is drawn well, it does seem a little bit wider than the parent functions. Our final answer should be negative 1/3 x minus 1 squared plus 4. We're welcome to plug in any values for x now and see what comes out for y, including, if you like, negative 2. I would challenge you to plug in a negative 2 and see if you come out with a positive 1.